So in questions 1 and 2, you have to find the number of possible outcomes in the sample space and list all the possible outcomes. So if we roll 3 dice, how many possible outcomes are there when I roll 1 dice? 6. But I'm doing it 3 times, so if I roll it again, how many possible outcomes do I have? 6. And if I roll it again, how many possible outcomes do I have? 6. So we would do 6 times 6 times 6. And get 216. One way that we can show all the possible outcomes, so a different way of doing this question, is we write out all of our possible outcomes. We could roll a 1, 2, 3, 4, 5, 6. And then if we roll a 1 the first time, we could roll a 1, 2, 3, 4, 5, 6. If we roll a 1 again, we could roll 1, 2, 3, 4, 5, 6. With a dice, when you have 216 possible outcomes, it's a lot of work doing it this way. But you could write it out with something like if you were to flip a coin. So let's say, so this is an extra question. Bless you. Oops, flip 3 coins. So let's say we had a question that said you flip 3 coins. Let's list the possible outcomes. So if I flip 1 coin, what are my 2 possible outcomes? Heads or tails? Then if I flip another coin, what are my possible outcomes? Heads or tails? But I could have flipped tails the first time, so my possible outcomes would again be heads or tails the next time I flip. And then let's say I flip, well, you're flipping 3 coins. So we flip another coin. What are my 2 possible outcomes now? Heads or tails? So all of these get another heads or tails. So how many possible outcomes do I have? 8. We have 8 possible outcomes. And each one of those outcomes comes from the tree. So one of them is I could have flipped a heads, heads, or heads. I could have flipped a heads, heads, or tails. I could have flipped heads, tails, or heads. Or heads, tails, or tails. What if this question said, what is the probability that you flip tails all 3 times? So look at our possible outcomes. How many did we have total? 8. We had 8 possible outcomes. Out of those 8, how many did we flip tails all 3 times? So like one of our possible outcomes was heads, heads, heads. The other one was heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. So how many of those did I have? Tails, tails, and tails, all 3 times. 1 this time. So 1 out of 8. This question could also ask, what's the probability of getting exactly 2 tails? So looking at our possible outcomes, how many possible outcomes total did we have? For the same question, 8. And out of those 8 possible outcomes, which one had exactly, or how many have exactly 2 tails? So we have one here. We had heads, tails, tails. We've got one here. Another one here. Any others? So how many? 3 out of 8. All right, let's look at number 2. A clown has 3 purple balloons labeled A, B, and C, 3 yellow balloons labeled A, B, and C, and 3 turquoise balloons labeled A, B, and C. The clown chooses a balloon at random. So the clown is just picking one balloon. How many balloons total do we have? What are our possible outcomes? So we have 3 purple, 3 yellow, and 3 turquoise. 9. We have 9 possible outcomes. We don't have to multiply it by anything here because we're only picking one balloon. The difference between 1 and 2 is that 1, we rolled the dice 3 times. So we have to multiply the possible outcomes each time we roll the dice. Here, we're just picking one balloon at random. So we have 1 balloon and 9 to choose from. So 9 possible outcomes. All right, for number 3, we changed the numbers of the question. So your friend has 5 sweatshirts. 2 sweatshirts are green, 1 is white, and 2 are blue. You forgot your sweatshirt, so your friend is going to bring you one. Is going to bring one for you as well as one for himself. What is the probability that your friend will bring 2 blue sweatshirts? So we're picking 2 sweatshirts. There's 2 different ways that we can look at this problem. We can write out all of our possible outcomes. So I have 2 green. I'm going to say green, green, 1 white, and 2 blue. Well, if he picks a green one, what are my possible outcomes for the next sweatshirt that he picks? I have green, white, blue, or blue. Same thing, if I pick a green one, my possible outcomes are green, white, blue, or blue. If I pick a white one, what are my possible outcomes? Green, green, blue, or blue. If I pick a blue one, what are my possible outcomes? Green, green, white, or blue. Perfect. And if I pick a blue one, green, green, white, or blue. How many total outcomes do I have? Out of those total outcomes, how many are blue and blue? So we've got 1 here, 1 here. So how many? 2. So 2 out of 20, which would simplify to 1 out of 10. So that's one way that you could do this question. Any questions there? Another way that we could do this one is by multiplying to find our possible outcomes. So the first time he grabs a sweatshirt, how many possible outcomes does he have to choose from? 5. The second time he grabs a sweatshirt, he already has 1 in his hand. Now how many sweatshirts does he have left to choose from? 4. Now out of those 5, how many of those sweatshirts are blue? 2. We're assuming that he grabbed a blue sweatshirt, so now how many blue sweatshirts does he have left to choose from? 1. And you can multiply. So you can find the probability of each time he picks a sweatshirt and multiply them together. So we have 2 over 20, which is 1 over 10. So you could do this question either way. If it helps you to draw out the tree and see it, do it that way. If it just helps you to multiply, it's kind of similar to 1, but you're actually finding the probability here, not just the total outcomes. So when you're finding the probability, your answer is going to be a fraction. If you're finding the total outcomes, your answer is going to be a number bigger than 1. All right, let's take a look at 4. The estimated percentage student GPA distribution is shown. Find the probability of each event. So we have to find the probability a student chosen at random has a GPA of at least 3.0. So this group has 3.0, but, bless you, would my answer be 25%? Why not? Because it says at least 3.0, so I have to include everything more than 3.0 too. So I'd also include this group, which is 3.5 to 3.7. Anything else? 3.8 to 4.0. So then I just add all the percents together. I have 25% plus 12 plus 7. So that would be 44%. Let's look at B. A student chosen at random has a GPA between 1.0 and 2.9 inclusive. So it just means that it's including those numbers. So what percentages am I looking at here? 1.0 to 1.9. So 9%. Anything else that's included in here? Awesome. 2.0 to 2.9, so 41%. We add these together, we get 50%. So we don't include this one, even though it looks like it would be because it says 1.0. This is saying less than 1.0. So it's not included in between 1.0 and 2.9. Okay, number 5. A bag contains the same number of each of 4 different colors of marbles. A marble is drawn, its color is recorded, and then the marbles placed back in the bag. This process is repeated until 40 marbles have been drawn. The table shows the results. For which marble is the experimental probability of drawing the marble the same as the theoretical probability? So let's find our theoretical probability first. So theoretical probability is as if each thing is equally as likely as being picked. How many different color marbles do I have? 4. So what are the chances of picking a yellow out of those 4? So if I am equally as likely of drawing any color out of those 4 different colors, 1 out of 4. It's an equal chance. For theoretical probability, it's equally as likely. I only have 4 colors, so I have a 25% chance of getting any one of those colors. So theoretical probability of picking red would be the same. Of picking blue is the same, and of picking black is the same. Now our experimental probability is when we actually use the table to find how many times we actually picked that color. So what's the experimental probability of picking yellow? 12 out of how many? 12 out of 40. I picked yellow 12 times out of the 40 times that I picked a marble. Can I simplify this fraction? So 4 goes into both of them, so it'd be 3 over 10. Is that the same as the theoretical probability? No. So let's try red. So what is the experimental probability of picking a red marble? 10 out of 40, which simplifies to what? 1 out of 4. Is the experimental probability of picking red the same as the theoretical probability? So what do you think my answer is going to be? Red. You can keep working and find the experimental for blue and black. So for blue, it'd be 7 out of 40, which doesn't simplify. And then for black, it would be 11 out of 40, which doesn't simplify. So the only one that's the same would be red. All right, next page, we're looking at 10.3. So for the first 2 examples, it gives us the totals, so we don't have to worry about finding the totals. But if it didn't, just like the notes from yesterday, you could always just find the totals of each category. So for A, it says, if a person was selected at random, what is the probability that the person is an advanced surfer? So what's the pool that we're picking from? We always want to see what our total is. So a person was selected at random. 205. We don't have any restrictions on who we selected, so we selected anybody that was surveyed. 205. What is the probability that the person is an advanced surfer? 42. We have 42 advanced surfers out of the 205. Just be super sure that you can't simplify this fraction, or you could always leave it as a decimal. So we have 42 divided by 205, which would be 0.204, or you could say 20.4%. So for B, it says, what is the probability that a randomly selected female is an advanced surfer? So we're randomly selecting a female. So what number is going to go on the bottom? 95. We have 95 females. And out of those 95 females, how many are advanced surfers? 18. So we have 18 over 95. Let's simplify this. We can make it a decimal. So 18 divided by 95 would be 0.189. Or you could say 18.9%. All right, let's look at the next box. So it says, what is the probability that someone with a fishing license does not have a hunting license? So we're looking at somebody with a fishing license. How many people have a fishing license? 242. So 242 would be our bottom number. Out of those 242, how many do not have a hunting license? 177, perfect. Let's put this in the calculator to divide. So we get 0.731 or 73.1%. Your number on the top is always going to be smaller than the number on the bottom. Your probability can't be more than 1, because then you're saying it's more than 100% likely that you would pick somebody. So just be careful. Your probability is always going to be less than 1 when you divide it. For B, if a person was not chosen at random, what is the probability? If a person was chosen at random, what's the probability that they do not have a fishing or hunting license? So a person is chosen at random. How many people did we survey here? 620. So 620 is going to be our bottom number. Out of those 620, how many people did not have a fishing or a hunting license? So let's say that they do not have both. This question's not super specific, so I'm going to change it. So they don't have both a fishing or a hunting license. So they have neither. Out of the 620, how many people have neither fishing nor a hunting license? Awesome, 341. Because we had to find how many people had both no's, so that would be 341. So let's divide this in our calculator. So 0.55, which would be 55%. For the next one, we actually have to find the totals. So how many adults total did we have? 73. How many students total did we have? 47. How many yeses did we have total? 63. And how many no's did we have total? 57. And then how many people were surveyed total? 120. Perfect. So let's look at number 2. Based on this data, use a percentage to express how likely it is that a student at a football game next Friday will not buy a program at the concession stand. So we're picking from what group? Students. So students is going to go on the bottom. So how many students total do we have? 47. So out of those 47 students, how many did not buy a program at the concession stand? 26. We had 26 no's. So then we can do 26 divided by 47. We get 0.55. What would this be as a percent? 55%. For 3, based on this data, use a percentage to express how likely it is that an adult at the football game next Friday will buy a program at the concession stand. So what's the group that we're looking at here? Adults. So how many adults total do we have? 73. And out of those adults, how many will buy a program at the concession stand? 42. So 42 divided by 73. So we get 0.57, which would round to 0.58, which would be what percent? 58%. Right, and then for 4, based on this data, use a percentage to express how likely it is that an adult or student at the football game next Friday will buy a program at the concession stand. So how many adults and students do we have? 120. Out of those 120, how many adults bought tickets or bought a program? 42. And then how many kids? 21. So how many people total bought a program? 63. So 63 out of 120. So that would be 0.525, which would be 0.53. So what percent? 53%. On the next page, number 1, you randomly draw a marble out of a bag containing 8 green marbles, 4 blue marbles, 12 yellow, and 10 red marbles. Find the probability of drawing a marble that is not yellow. So first thing we want to do is see how many marbles total do we have. So we add them all up. How many marbles total? 34. And out of those 34 marbles, how many are not yellow? How many? 22. So our probability would be 22 out of 34. So you can leave it as a simplified fraction or change it to a decimal. So it would be 0.647. Or we could say 64.7%. If you leave it as a fraction, make sure it is simplified. Here, this would have to be simplified to 11 out of 17 if you wanted to leave it as a fraction. All right, let's look at number 2. So we have to find the probability of A bar, probability of not A. So what would we do here? Anybody remember? You do 1 minus the probability. So we do 1 minus 0.32. We would get 0.68. That's it. Just 1 minus the probability. For number 3. We'd do 1 minus the probability, so 1 minus 8 over 9. How do I add fractions or subtract fractions? What do I need? Same denominator. So I can make 1 9 over 9, and that would be 1 over 9 when we subtract. And then lastly, for number 4, we do 1 minus 0.01, which would be what? .99. Don't forget, probability is never negative. What else is it never? It is never more than 100%. So if I found the probability of something and got the decimal and it was like 1.5, you did something wrong. You're not going to have 150% probability of something. So it's never more than 100%. Your decimal is never going to be more than 1. It's also never negative. Right, we're going to do one more, number 5. You roll a 6-sided die 30 times. A 5 is rolled 8 times. What is the theoretical probability of rolling a 5? And what is the experimental probability of rolling a 5? So let's find our theoretical probability first. Theoretical is if we have an equally likely chance of rolling each number. So what are the odds of rolling a 5? Just randomly. 1 out of how many numbers do I have total on the dice? 6. So this would be my theoretical probability. And then for my experimental probability, how many times did I actually roll a 5? 8 times. Out of how many times did I roll it? 30. Can I simplify 8 over 30? We can make it 4 over 15, or you can just change it to the decimal. So you could do 8 divided by 30, which would be 0.266. You could say 26.6%. If you rounded it to 27, that's fine too. So any one of these would have worked for the experimental probability. And then skip number 8. We skip that in the notes so you don't have to do it. There won't be one like that on the quiz.